Yes, thanks very much for this opportunity. I just also want to thank my co-organizers and Wits University for hosting this wonderful event. So Nyalleng and I will be speaking about the fundamentals of machine learning. This is the first tutorial of this Indaba. After this, there will be practical, as you should know. So this is just kind of to prepare you for that. Now, so basically what this tutorial is going to be about is we're going to take a long or a huge step back and start on page 1 of machine learning. So really this is meant to be a very gentle and intuitive introduction to machine learning, mostly aimed at those of you that are fairly new to this field. I hope there are a few of you out there. Yeah, so really just to get things started, we wanted to just keep it very simple. And that is basically what I just said. Of course, machine learning is a very broad field. There are lots of things that we can talk about. So I want to apologize right now for maybe brushing over some important issues, or I will also skip quite a lot of things that you might feel is important. So sorry about that. Okay, and the tutorial is basically structured like this. We're going to start just by making sure we know what is machine learning, why does machine learning exist, and where do we use it. We'll go over a few typical basic machine learning tasks. And then I just want to say a few words about optimization and probability, which I think are two very, very important aspects of machine learning that are often overlooked. And then Nyalleng will take over and talk about some practical issues when we do machine learning. Okay, so I'm a mathematician by training, so before I start talking about something, I like to define that. So maybe I should try, this is going to be really difficult, but I'm going to try and define what I think machine learning is. So I think it all comes down to we want to give a computer the ability to find structure or patterns in data. That's really what it's about. And the reason why we want to do that is for the machine to understand what's going on, and also to predict what will happen in new situations. So that's really what I think machine learning is all about. I think you can also view it as a mathematical modeling process. So we want to construct mathematical relationships, let's say, between inputs and outputs from examples. And of course, the idea is that we want to generalize in a way that we can use these mathematical relationships to say things about examples that we haven't seen before. Okay, so I think that's the key aims of machine learning in a very simplified way. Okay, so I'm sure I don't have to convince this audience why machine learning exists, but basically the fact of the matter is that many problems that we are interested in these days are very complex and difficult. High dimensions, if you think about computer vision, natural language processing, really complex problems that would be really difficult for human to, let's say, hard code. So the idea is really to throw data at the machine and let the machine figure out what's going on. Of course, what's also nice about a machine that can crunch numbers is that it can find hidden structure in data. So this would be, if a human looks at the data, maybe there are some subtle structures or patterns that we can't see, but the computer can extract. And then, of course, as we all know, data is everywhere, and it's, there's so much of it all over, and of course also with the cloud, it's very cheap now to store data and to perform computations, so it's really now is a very good time for all scientific disciplines to start using machine learning. And now, at this point, I just want to do a little icebreaker, maybe a bit of audience participation. So I said that many different scientific disciplines now make use of machine learning. So I thought I'd ask you guys to give me an indication of how many different scientific disciplines are in this audience. So maybe, and this is also for the rest of you to see the makeup of this audience, because I think there's quite a lot of people from quite a lot of different areas. Maybe I think there are a few astrophysicists here, yes, and maybe people from the biological sciences. Oh yes, quite a few. Anybody from the social sciences, maybe? We'll get there, we'll get there. Yeah. Mathematics, yeah, pure mathematics, yes. Applied mathematics, engineering, mechanical engineering. Whoa, whoa, there we go. What else is there? Anybody we're missing? Statistics, of course, yes. Yeah, definitely. Finance, maybe? Yes. Economics. All right, awesome. So, yeah, no, definitely. The exception of social sciences, everybody's really represented, and this for me is an indication that there's definitely interest in machine learning, deep learning, all across disciplines. All right, that was my quick experiment. Okay, so as I said, I think machine learning in many ways can be seen as a modeling process. And of course, the first step for machine learning would be to start with data. So we would somehow get data from wherever. And then, of course, we have to decide what do we want to do with this data? What do we want to learn from the data? What aspects of the data do we think are useful for this? Things like that. Then, of course, the very important thing to do in modeling is to make some assumptions. Whether you do that explicitly or implicitly in the models that you choose or the relationships that you think are present in the data. So you pick a suitable model or algorithm. Then, of course, there might be some training, so that is where the machine learns from the data. Then, of course, we want to see how successful was this training, so we would have some sort of performance measurement. How well does the model generalize, of course, the important question. And then what usually happens with mathematical modeling is that we then go back. So in a sort of iterative way, we can then say, well, we're not very happy with the way that it performed, so maybe we should go back, get more data maybe, get the data from a different source. Maybe we should rethink what we think can be learned from the data, which aspects are useful, maybe not the ones that we thought are useful. Should we make different assumptions, pick different models? We train again, we test it again, we see if we're happy, and we go back. So it's always just an iterative process. Okay, and of course you find this in any mathematical model. So we have to make assumptions to turn the problem into maths. We do the maths, and we see what we get, and then we might go back to our assumptions. Okay, so of course there are different, I call them paradigms, I don't know, of learning. The first one can be supervised learning, so this is where we have set of input-output pairs. We're trying to figure out what should we do with the inputs to get the outputs, and we learn from examples with the idea to then predict output for new inputs. Unsupervised learning is, of course, when we don't have examples of inputs and outputs, so we want to discover patterns by just looking at the raw data. Then there is also things like reinforcement learning. I think we're going to spend almost an entire day on this, so I won't say too much about it. But basically, here we want to learn strategies or actions to take in situations based on some sort of reward that we get. So there's a feedback while training is performed. Semi-supervised learning is, of course, when you have a data set, but only some of the data is labeled. So you can, of course, learn from that. And then there's, of course, also deep learning, which I think is any of the above, but of course with very complex models and lots of data. And by very complex, I don't necessarily mean it's difficult for us to understand or interpret. I just mean it's got lots of parameters. Right. Let's just quickly look at some typical tasks. So this would be the regression, classification, clustering, all of those things. So in regression, of course, we want to fit a functional relationship between inputs and outputs. So if X is the input and Y is the output, we have some data samples, and we want to estimate the function that goes through. Some examples where this can be used is, of course, in weather forecasting. So we, for specific, let's say, measurements of the climate, can we fit a continuous function to make predictions about any measurements that we might have. Of course, also the classic house pricing prediction, and then also in epidemiology, disease, the study of disease spreading. So regression is, of course, an example of supervised learning. So we have the inputs and outputs that we want to fit the function to. Classification can also be supervised. So the idea is basically that we want to learn how different classes of data is separated. So this is an example of the famous ImageNet, huge databases of images, and every row is a class. So we want to use these to learn, for example, what does a photo of an elephant look like, so that if we give the system a new photo of an elephant, it will be able to correctly put the label elephant to that image. This is, of course, used for visual recognition, for example, character recognition. I think we're going to have a tutorial tomorrow about that. Of course, also to classify emails as spam or not. Maybe also in diagnosis, if we look at medical data, is this data from a healthy individual or from a sick person? Clustering is an example of unsupervised learning. So the idea is to take a data set and group it into similar points that are similar in some sense. So this is an example of image. I don't know if you can see it. Maybe results from an image search engine where it's been results are grouped into images that are sort of similar in some sense, visually similar. And here, of course, we don't have any labels, so it's unsupervised. So we just take the data and see, can we discover these groups automatically. So there's a few examples of applications, maybe in insurance, to identify clients with similar risk profiles. We don't know what the properties of those are, but if we have enough data, then maybe the machine can discover these properties. Also, maybe in something like graph clustering, we can look for links between symptoms and diseases, or maybe to build visual dictionaries. So this is where, again, we give the system a large database of images, and it automatically identifies structures without us telling the machine what sort of structures we're looking for. Okay, then something like reinforcement learning. This would be, for example, to learn some sort of winning strategy to play a game like chess through constant feedback. So as the machine tries different moves, there's always a feedback about the outcome of that. And there's, of course, always uncertainty, because we don't know what the opponent is going to do, so that, of course, makes the problem a bit more interesting. So some examples would be in autonomous navigation. So if we send out the car into the streets and it tries things, maybe bumps into a few things, and in that way learn that it shouldn't do that. So that's this idea of feedback, of course. Oh, and there's also this kind of famous one that's about 10 years old, of a machine that completely automatically learned how to fly a helicopter, which is, of course, a fairly complex control problem. Again, by carefully trying out new things and seeing what happens, and in that way learn what it should be doing. Okay. And then there's recommendation systems. These things are everywhere nowadays. If you go on a dating site, maybe it recommends possible partners. Also, of course, Amazon or things like that. If you like this book, maybe you'll also like this one. And this is a kind of a very interesting problem, because you typically have maybe a table like this. So you have a few users. The users have given ratings to different books. But of course, not all users rate all books. And you typically have millions of books and lots of users and only a few ratings per user, so it's a very sparse set. And of course, you want to make useful recommendations by basically looking at something we call collaborative filtering. So that's where, for example, if two users like the same book and the second user like another one as well, maybe we can recommend that one to the first user, things like that. So this can become very interesting. Okay, of course, applications include recommendations of movies and books, or maybe which news articles that you will find relevant. So the whole idea here is to do this without asking the user too many questions. So we want to use knowledge from the population to be able to do these recommendations accurately. Okay, then I just want to say something maybe on a more practical level. So let's consider polynomial regression problem. So basically we just want to fit a polynomial to the XY data pairs. So we have maybe a functional relationship like this between x and y. There's, of course, these coefficients that we will have to learn. But there is, of course, also the question of what degree polynomial it should be. And that degree of the polynomial is what we call a hyperparameter. So these, the idea of hyperparameters and normal parameters, hyperparameters are things that we kind of have to fix before we start training. So once we decided what degree of polynomial we want to fit, we can then run our training algorithm and basically find these coefficients. So this is kind of the distinction between choosing a model and then fitting the model. And maybe we see that once we've trained for these coefficients, it didn't work so well, didn't generalize so well, so maybe we go back and pick a different hyperparameter. Okay, but there's definitely a distinction between hyperparameters and parameters. Okay, and then I think what is quite insightful in a way is to keep in mind that when we train, we really optimize. So we might have a set of parameters which we can call theta, let's say that's a vector parameters. The idea is, of course, to find values for these parameters. And when we train, we try to minimize some sort of error. So for a specific set of parameters, if I apply that to the input, I will get a certain output, and I can compare that output to what I should be getting. So there's going to be an error, and I'm trying to minimize that error in the simplest sense of it. So what we'll have to do to be able to do that is, of course, to define some sort of error function. This can be things like sum of square differences or cross entropy, things like that. And this is a function of the model parameters. So for a specific set of parameters, we can calculate an error between how the inputs are transformed with those parameters and what the outputs should be. And then we can do something like gradient descent to try and find optimal parameter values. So this is a very popular technique. This is also one that you'll be seeing in the tutorial. And in its simplest form, it's basically this equation. So what happens here is that we start with some set of parameter values. At the very start, we should have to initialize this somehow. And then in one iteration, we're going to calculate a new set of parameter values. So this is something that happens over and over. So we keep updating these parameter values according to this. And you can see what we basically do is we're subtracting some a scalar multiple of a derivative. So this derivative is the derivative of this cost function with respect to the parameters. This thing eta is what we call the learning rate. Now, let me just try and give you some intuition of what this means. So basically we have, our cost function is a function of parameters. So we can have lots of parameters, so it's a function in a lot of with a lot of dimensions. Or rather, it's defined in a high-dimensional space. And we want to try and find the minimum of this function. So we have to explore this space and try to find the minimum. A minimum is, of course, where the derivative is 0. And the idea with gradient descent, as the name suggests, is we want to descend this high-dimensional error surface, meaning that we want to move on this surface in a way that decreases the value of the function. And we can use the gradient for that. The gradient, of course, gives us an indication of the slope of the surface. So if we want to keep going down, we basically have to move in the direction exactly opposite of the gradient. Okay, so that's the negative of the gradient. And this learning rate obviously controls how quickly we move. There's a delicate balance between moving too quickly and moving too slowly. If we move, okay, so we basically want to end up in this minimum of the error surface. So we start somewhere up here and we try to move down the hill towards this minimum. If we move too quickly, we might accidentally jump over the minimum. That's not what we do. And on the other hand, if we move too slowly, we might never get to the minimum. So, this is also why we usually update the learning rate as these iterations progress, and this should help with convergence. Now, the useful thing about thinking about or reminding yourself that you're busy with an optimization problem is that you can fall into all the pitfalls of optimization. So, for example, local minima. So your learning algorithm might spit out an answer, and it looks like everything converges nicely, and we're at a very nice point where the derivative is 0, so it looks like a minimum, but it might be a very bad minimum. So this is the idea of local minima, and of course some ways to try and get around that is to train multiple times at different starting conditions. Of course, it's also possible to converge to something that is not yet an optimum. If our learning rate becomes too small too quickly, we might actually converge to a point that is still on the slope of going down. So again, it looks like convergence, but actually we're not converging to the correct thing. Okay, so that is how we should look at training as an optimization problem. Of course, this gradient descent is very simple here. We get adaptations of this. So, for example, stochastic gradient descent would be if you have a very large data set or many parameters, this quickly becomes very expensive to evaluate. So the idea with stochastic gradient descent would be to sample randomly which parameters you actually do this, and so you basically take a sample of your parameters to do the gradient descent instead of always using all of them. Okay, and then the other thing that I thought just to quickly mention is this the aspect of probability. This, I think, is also something that a lot of people sort of ignore or not really aware of, especially users of machine learning. We are all creators of machine learning, but it's very easy to run a training algorithm on data and get an answer and never really thinking about it in terms of probability distributions. But I think it's very important to think in terms of probability distributions. It can be very useful to gain understanding of what it is that you're actually doing. It can also be very powerful to exploit the fact that you're manipulating probabilities, and especially in things like Bayesian networks, you can combine all these probability distributions in a very nice way to do things like inference or reasoning under uncertainty. Okay, so the fundamental thing, I think, is that when we have a data set, we can think of the data as being sampled from some sort of underlying probability distribution. And it's, for example, very important to be aware of the fact that we're usually assuming that the data in our training set and the data in our test set come from the same distribution. If we're not willing to assume that, then we're in a bit of trouble. So the idea is, of course, to use the training set to train a model that will fit our test set well, or unseen examples well. So we have to assume that our training set is a good representation of things that we're expecting to see in the future. Okay, and then there's these things of discriminative modeling and generative modeling. So if we're doing something like classification, we have samples, X, this is our data, and we're trying to estimate labels for them, which class does the data belong to. So this would essentially be a maximization problem like this, where we're trying to find the labels that maximize this probability. So the probability, so given X, given the data sample, the probability that that sample has this label should be high, of course. So when we do classification, even though we don't really maybe not realize this, we're solving a maximization over a conditional probability like this. And this is what we call discriminative modeling. So we're basically directly looking for the labels that maximize this condition. Then we also have, then we also have generative modeling. So the idea there is to basically try to model the distribution of the data. So we're basically trying to find this joint distribution of the data and the labels. So it's a kind of a different way of thinking about this. But these two equations are actually will give you the same answer. So instead of directly trying to find the boundary between two classes and using that to classify new data, we're trying to model the distribution of the classes. And if we then get a new data point, in discriminative modeling, we would take our decision boundary to decide which class it belongs to. In generative modeling, we would basically take our data point and match it to our distributions of the classes and see which one gives us the highest probability. So that's kind of intuitive. Yeah. And as with many things in machine learning, it's impossible to say which one is better than the other one. There are definitely problems for which the one works better than the other. Okay, so without any technical detail, what I just want you to do is to, as far as you can, try and write down things like this for your learning problem. What are the probability distributions that I'm working with? What are the ones that I'm going to require? Here I see, for example, this is a prior distribution over the labels. So is there something that I should be thinking about, trying to write down, and all of that? Yeah. Okay, so just a very quick word on the practical that will follow this tutorial. So we're still keeping everything very, very simple. Of course, after this, for the next tutorials and the days to follow, we're going to get to all the strange and wonderful things. But for right now, we just want to get everybody off to a good start. So our practical is also meant to be quite simple. It's quite long, but it is quite simple, actually. What we're going to ask you to do, I don't know, maybe some of you have looked at it already. It is basically a simple linear classifier to implement. So in 2 dimensions, so you're going to generate a training set, points in 2 dimensions that are sort of clustered around here, points are that sort of clustered around here, and then we're going to try and find the boundary between these 2 classes so that we can classify new examples. A linear classifier, of course, means that the boundary is a straight line in this case, and the way that you're going to do that is to minimize something called the cross entropy. That's a cost function through gradient descent. So we'll look at all the mathematical detail of doing gradient descent. You can, of course, just simply run a Python script, a Python function that does this for you without having to worry about all the details, but it is very useful to just go through that exercise and make sure exactly what it is that you are busy doing. So we can, for this example, we can write down the gradient on a piece of paper mathematically, and then see what happens when we do this gradient descent. So of course, linear data, linearly separable data is not really very realistic, so we'll then move on to nonlinear data. So we're going to see if we can run our linear classifier on nonlinear data. So this is data that cannot, or classes that cannot be separated by straight lines. So that won't work so well, and then we're going to introduce a nonlinear activation function to basically turn our linear classifier into a nonlinear classifier. And it's pretty amazing how the machine can then learn these nonlinear decision boundaries. Okay. So now I'm going to hand over to Nyalleng. She'll be speaking about a few practical issues and aspects of machine learning.
Hi guys. I'm quite impressed by the attendance given yesterday, but we're all here, so that's a good thing. I'm Nyalleng, as I've been introduced. And today I am just going to talk a little bit about some of the things to think about as you're going through and doing some analysis, some real practical things that might come up, or to just keep in mind. So the first thing is, all of this starts off with data, right? Machine learning, everything, as they say, your model is only as good as the data you have. So it all starts with the data. You need to make sure that your data is representative. You need to make sure, so if you're solving a problem for a certain demographic, you need to make sure that your data covers all of that demographic. Otherwise, you're going to be applying a certain model that you tested in one space to the other space, and that's not as useful. The second thing I want to talk about is going to be on the models and training. So how do you choose a model? This actually comes up quite a bit, especially with people that are just getting started. In time, you'll build some intuition about, what you think is going to work well and all of that. But we're going to start off with just a little bit of, once again, this session is about building intuition. And for some of you that have been working in this for a bit, this might be, you like, been there, done that, got the t-shirt. The next thing, then the last thing we'll be talking about is improving your model. How do you evaluate your model? How do you test it? How do you verify it? Something that's very important, that we see a lot of results going out, claiming something, but when you check on the statistical basis of that claim, sometimes it just doesn't hold, which actually is a really good thing to always work with statisticians. And actually, also really good to work with domain experts. So that's why it's a shame that there are no social scientists, because a lot of the problems we want to solve affect communities and humans. Anyway, the data. So you get a data set, you collect this data set, which I'm a data scientist, and actually this kind of becomes like the really hard part, because people don't want to release their data, because once you have their data, then you know a lot of their secrets, and they don't always love that. But anyway, so you get your data. It's a good idea to eyeball it, have a look at it. How big is it? What are your bounds? What are your margins? Get to know, is it dirty? Do you have missing data? What are you going to do if you have missing data? And that's actually, this is a very important step, because a lot of the time this is where we introduce our own bias as machine learning practitioners, which once again goes down to why we should all participate in this area. Because if we all introduce our bias, then hopefully we will capture the whole space of bias, right? But anyway, so, and it's also really important, once again, to get domain experts in this area, because you don't want to solve a problem and then you realize, well, this is not viable. So I work with biologists, and sometimes there are viable biological structures. So I can't just say, well, I predict that this protein structure is going to be like this, and then it's just not viable, because it's just not how the body makes things. All right, then the next thing is you need to pre-process your data. You need to transform it in some way. So once again, borrowing from my proteome work, we get a lot of data that shows you the spikes of each one of the chemicals that are there, and then you take each one of those, so it's like a print, it's like a fingerprint, and you have to take that print, map it onto a database, and that's going to tell you which protein is most likely there. So now I actually have to transform the raw data into some kind of comprehensible data, even before then moving it into a graph structure where maybe I want to know how these proteins interact. So that's the part about pre-processing. We're going to talk a little bit more about that. You might want to remove some outliers. Once again, you are introducing your own bias. So all this pre-processing, whatever you do to the data, starting from the data you actually choose to start working with, you are introducing your bias. And I think that's a very important thing to always remember as we go on and say we're doing science, and science is clean and objective. Okay. Now, so once again, the other transformations that you might have to make to your data, so for example, if you know that the algorithms that you're targeting, the algorithms you're going to be working with, only take in numerical data, you might want to transform some categorical data into numerical spaces. So for example, using one-hot encoding, that could be that, as this example shows. But sometimes you actually want to go the other way around. So for example, if you're going to be implementing a decision tree, you might actually want to take your continuous data, chop it up, and make it into some categories, and then you can use it in your decision tree, into your basic decision tree. Okay. Now, I've actually already talked about this, where you actually take some raw data and you transform it into some data that is easier to interpret. And this can be good, because this first step of the data, of looking at the data, is to build intuition. Is to build intuition about what is available to you. What can you do? What kind of analysis can you do given this data? What kind of problems can you solve given this data? So once again, if you can transform data that is all kinds of just rambles and transform it into something that has more structure, you'll find that you can actually do better work. All right, this is a statement I am here to be corrected about. This is open. Some people will say you can't go anywhere without making sure that you have selected the most powerful features, the most discriminative features. And other people say, well, isn't the whole job of machine learning, or actually deep learning, to be that you throw the bucket at it and the machine should be good enough to decipher what is true and what is not? So, pick your path. Like I said, a lot of what I'm going to be saying is just think about it as you're going through. But anyway, So we do a lot of feature engineering in data science, and one of the problems is because we never have too much data to be able to say, we're going to throw a bucket, and the machine will be able to understand everything. So when you don't have a lot of data, you want to get the strongest, the most discriminative good, because I was thinking discriminant, and that's the wrong word, but discriminative is the right word. So you want features that are discriminative, you want features that actually store information. I have a feeling a lot of you have seen decision trees, and you've gone through the basic decision tree of how you construct the basic decision tree. So if you think about a decision tree and the whole idea of information gain, this is what we mean. You want features that are going to add to your information, the information you already have. So, I thought that information was there. Anyway, so what you want to do is, so if you think about the process of the decision tree, it's going to, first of all, pick a feature that's going to give you the biggest chance of shattering the class, right, into yes or no if you're working in a binary class. So you want the features that are going to help you, if you're working in classification, to quickly help you to say, this is a tree, this is a horse, okay? So for example, perhaps the color brown is not going to help you too much because trees can be all the way brown and horses can be all the way brown. So that's not a very good, the color brown, if that was there in your data set, it's not going to be the most descriptive of features. The other thing that you want to think about in terms of informative is, if I want to know, so if I want to study a difference between two things, so for example, I want to study the difference between a cancerous cell and a non-cancerous cell. If I already know that feature A and feature B behaves about the same between the two classes, right? There's a strong correlation between them. I don't need to keep both. I just need one of them. Because if I have one, I know how the other is going to perform. And this is actually a really good thing to do, to actually drop off some of these features because you're reducing your dimensions, which some of you and a couple of you, and the intuition would be that if you have highly dimensional data, you're going to have a more complex machine and you're going to take longer to train, you're going to take everything. So the smaller and simpler you can get your machine, the better. So if you don't need a feature, do away with it. So exactly how do you do about it? I'm sure the computer scientists and the engineers in here already can tell that this is a problem that can be quite complicated, and one of the simplest strategies would be an NP-complete solution, right? Where you test every feature and you get to see, does it work, is it great, do I add it, and all of that. But what you can do is, you can actually go through and you can drop one feature at a time and then test for each one of them, have I lost too much information? Okay, so you have your whole set of features, drop one and see, is my data have I lost too much information? Can I still recreate the original data set given the one less data set? And if you can, for the most part, so if you can still identify that this is a tree and this is a horse, then you do away with that feature. The other thing would be, of course, the alternative to this is you start with one feature, you measure the information that's stored inside that feature, you add another feature. If it adds significant amount of information gained, then you keep it. If it doesn't, you do away with it, which kind of borrows from that first line. Then the second way is to, which actually we use PCA quite a bit for that, is to find the features that have the highest variance, which means they capture the biggest difference in the data points. So if you have a cluster of all these points all together on one dimension, then that dimension doesn't have very high variance. So you want to find the dimension or feature or whatever column that has like the highest variance, and that's the one that you want to keep. Yes. Mm-hmm.
And you drop them, but you've already trained your model.
Mm-hmm.
I mean, obviously, if you just measure correlation,
mm-hmm.
that's another story. But
mm-hmm.
it sounds like as if you have to actually have your model already trained to drop the features. That would make sense.
You don't need to necessarily do that. So you can measure by that thing of saying, can you recreate the original data set? So for example, if you think about compression methods, right? The idea is you can compress your data, right, to have fewer features, but you can still recreate the original. So the way like images are compressed, you compress it, you store fewer bits, but you can still see this was an image of a tree. So that's the idea there. So can you still recreate? That's what we measure before you move on onto the model. But yeah, that's, yes.
Not sure I missed this, but is the removal of the features, is it with replacement or without replacement?
Okay, so what you want to do is you want to get to as few features as possible. So without replacement is good. You only keep them if you absolutely need them. Okay. Yeah? All right? Uh-oh. Uh-oh. Yeah. Yes. Okay. I'll take the last question. On the same slide, I imagine. Yes.
Yes. So asking about the low variance.
Uh huh.
So if you have a feature that's saying thermometers,
Uh huh.
feature immediate, the thermometers, it seems like that is automatically getting more variance, regardless of its predicted capabilities.
Okay. So the idea behind the variance is to say, so you want to see how it really borrows from the word vary. What's the thing that makes my points different? So in some application, yes, distance will be the thing that makes your points different, but in some areas it won't be. So for example, if you think about this country and the population and people living everywhere, right? And you wanted to understand maybe what leads some people to be more educated than others. I'm not sure distance is gonna be the one, but maybe income is gonna be the one that has the highest variance. Okay? So it's just about the thing that explains the differences, the dimension that explains the differences in your data. Okay. All right. More on the transformation. Rescaling your data, quite a lot can be a really good idea. So making sure that your data kind of sits on the same scale. So for example, what you have here is you've got really, really small numbers for the bedrooms. If you were looking at, let's say, census data, you've got really low numbers there, and you've got very high numbers when you're talking about the size. But if you just want to understand what the distribution looks like for each one of these, right? It's a good idea. So what I've done here is mean centered it and just gave it a variance of 1. And that way, they're sitting on the same scale, and you can quickly, so you won't have a problem of your algorithm sometimes getting swayed by what it thinks is an outlier, because they're all sitting on the same scale. Okay? So it can be a really good idea to transform that. So for example, this is actually, if you're doing fairly simple PCA, this is very important to actually mean center your data if you're going to be doing PCA. But actually, this information probably links a little bit better to the one we're talking about how you can reduce dimensions. So for example, you've got that, you project it onto the line, and you want to, onto a dimension, and you want the dimension, once again, that captures the biggest variance. So just to answer to that, as you can see, that's the thing that shows the biggest distance. If you were to plot a vertical line that comes down like this, right? A lot of these points would sit very close to one another, right? If you look at them on the y-axis, they would all kind of sit very close to one another. This one, this dimension of going diagonal is the one that gives you the thing that makes it the most different. So you do that, you project it onto that, and you also want to make sure to minimize how far away you're projecting onto. So you could think about this and say, what if you were gonna go the diagonal this way? Right? You would still maybe not have as much variance, but also all of those points are going to be very far from the origin line, which you don't want. But I'm sure quite a lot of you have seen PCA before, so once again, just gonna rush through it. And so you transform this whole thing from from 2 dimensions onto a 1-dimensional scale, and now we're just working with a line instead of X and Y. Okay. This is something that sometimes makes people unhappy, which is that quite a bit after you have transformed this and onto the principal components, it's not as easy to know what it is. Because at first, we knew we had we had height and weight, but now we've got this new dimension that we don't exactly know what it is, but anyway, that's just that. All right, oh, I really need to pick up. Models and training. How do you choose a model? This is pretty much what it is. And you choose a model based on the problem you want to solve. Also based on the data you have. If you have a lot of data, you can go big. If you have a lot of data and you have very powerful machines, you can go pretty big. You can go on and say you want to do apply deep learning to solve your problem. But if you have very little data, maybe that won't be the best. The other thing is, do you want your output to be a continuous, or do you want it to just be like a yes or no type answer? You also, so you have to think about how complex do you think is going to be a model that captures what you want to study. Now, the best thing always is to start with the simplest model. If you don't already know that this is a really complex problem that's going to need all the machinery thrown at it, start off linear. And today's practical, you'll see, you're going to start off linear, and then you get something, and then you realize, okay, maybe linear doesn't exactly work for me. Then go to maybe higher dimensional polynomial, and so on. And then the model can get more and more complex. If you're working with neural networks, start off with a perceptron, which is just a single layer. And if that doesn't work, add more layers, and so on until you get to a point that you're happy with, which we are going to talk a little bit about. So once again, you have to decide, am I doing a regression problem, which is y equals to fx on a continuous scale? Am I doing classification? Am I going to draw like a boundary line that says this is class A, this is class B? Is that the solution you want? Am I going to do clustering? There is a lot of these, and once you get more and more into these algorithms, like I said, you start to build some intuition. So am I going to want something that feels like it's got like an embedded number of layers, like a neural network or a decision tree? Or do I want something, because on top of this, sometimes you build a model, but you have to interpret it and then report it to whomever your client is, okay? And sometimes it actually is useful to have a really simple model that is really easy to explain to people that are not machine learning practitioners, okay? So that's also something that you might want to think about. So basically, no one model is necessarily the best for all problems. You have to engage with the models. Anyway, and as Willie has said, this is an iterative process. Sometimes you start off with a certain model, and then you realize that's not going to work, and you deploy another one. And actually, a lot of the time, you will find that you're running about 3 models at a time, and then compare whichever one is going to be the best. So it's the process of selecting your model itself is an iterative process. But you have to sort of have some intuition about where to start. Otherwise, you're going to run through all the many machine learning algorithms to get to that. Okay, how do we measure performance of a model? Okay, the classic thing, you get your training data, you get your testing data, right? You divide it up. So you train, the model learns the features from the training data, and then to test how good your model is, you apply it on the test data, which is data that the model has never seen before. Because you want to understand, does the performance that I observe while I train this model generalize to unseen examples, right? Because the whole point of making this model is so that the model can take over after a while, right? You train it, and then you say, well, do the work for me. So you need to make sure that it does generalize to other unseen data, okay? All right. Okay, so in order to do that, so you kind of actually have two types of test data when you're training. You've got the validation test, which is the one that you keep validating your model in as you're tuning your parameters in order to see how am I performing, am I good, and you test that against the validation test. Once the model is complete, then you test that against the test set, okay? One of the most common way to go about this model training is what we use, the K-fold validation, which means you take your training data, You take a section of that training data and you keep it aside. Let's say you take 20% of that training data, put it aside, you get 80%, you train your model on it, learn all the weights or the parameters and the coefficients for that model, and then you test it against the 20% you set aside. And you keep doing this, and so you chop up your data set. And you don't need to actually test against all partitions, because remember, as Willie said, we have an assumption, which is that there is a probability distribution that governs this model, that all this data, that generated this data. So you can just consistently resample with replacement 20% of your data to be your validating test, until you run the number of epochs that you feel you're comfortable with. Okay? All right, so that's that. Now, how do you know that your model is good? How do you measure performance? How do you know that, okay, I'm good, I'm deploying this, I'm going to sell this out, I'm going to tell people that, hey, now you can use my model to say, hire person X, or give a loan to person Y, or these big things that have consequences at the end. Their model has got to be verified and validated. All right, so in regression, you can always use a version of some kind of like a square error, least square error, some sort of like a measure, which is to say, how far are my points from the regression line? So remember that PCA thing, if you could also look at it as a regression line, and you just want to measure and say, what's the average? On average, how far are my points from where I have predicted them they're going to be? And that would be for that. For classification, we use a little bit of a measure of true positives and false negatives. So a confusion matrix is going to tell you, oh God, the logic of that. Okay. So a confusion is going to tell you how right you are and how wrong you are. It's going to tell you those measures about, like, if, for example, your true positive versus your false positive, and anyway. Somebody, I'm sure you know what it is. And then, of course, there's, no? I actually am assuming you know what it is. Okay, Google knows what it is, so. This is my moment of, it's just too mangled up. I can't deal with it. It's just this grid, and yeah, it helps you just understand what kind of wrong you are. Are you wrong because you say things are true when they are not true, or are you wrong because you say things are false when they are? That's that, okay? Anyway, then you have got, for example, you look at clustering. So one of the biggest in the intuition with clustering is you want to make sure that what you call a cluster is as tight as possible and as far away as the next cluster. All right, so that's what this sort of like density, for example, would measure. How close are the points that I call my cluster? And then, of course, what's the distance between them and the next cluster? Because you need to be able to draw that decision boundary and say, this is cluster A, this is cluster B. This is kind of tricky because you have to decide what's the threshold. Because if you loosen up the threshold of how tight the cluster is, then the cluster grows bigger, right? And if you make it really small, then the cluster is really tiny, and you might be missing out on some of those relationships because you don't think they're in the same cluster. But you decide, like I said. For me, it's just you decide. And then, of course, in recommender systems, you can use click rates and ranking, so people will say, thanks for the book, I like it, I give it a 2, I give it a 5. Like, people don't hardly go to restaurants anyway these days without looking at, what people have said about it. If it's below a 4 out of 5, you start thinking otherwise. Okay. So a really important thing, which actually is part of that kind of confusion matrix of what kind of wrong am I okay with being, okay? So it's to think about this sort of thing. So we worked on a project on rhino poaching last year, and for us, we gave our model a harsher punishment if it missed a poaching versus when it said there was gonna be a poaching and there was no poaching. Okay, so you don't just have to say, I got 90% wrong, and I got this morning, I got 90% correct, and I got 10% wrong. You actually have to think about what's the implication of that 10% wrong. Can I really tolerate that 10% wrong? You see this a lot in medical spaces also, where they would rather not tell you you have disease X than tell you you have it, and then you don't have it. Because knowing you have disease X, especially deadly disease, people's lives just go down. You really actually affect people's lives. So they really would rather say, well, I don't see it, maybe come back in 6 months for another test. Okay? So you actually skew the error function intentionally, given once again that domain knowledge, which is why we don't work alone. Okay, then lastly is to say, what's the statistical significance of my result? If you come in here and you test like 20 people out of the 300 so people that are here, and you say members or attendees of the deep learning Indaba are X, and I can therefore take my model, deploy it to all of the future deep learning Indaba people coming through. Yeah, I think the statisticians in this room would not like you very much. One of the ones that we always fall into is the whole thing of correlation and causality, right? Just because they seem to be behaving together, it doesn't mean that one makes the other happen, all right? So it's a really good idea to make sure that your model also holds statistically, right? Because it's the bearing of everything we do. The whole thing of probability. You always say, I am correct with this much probability, but you also need to make sure that you have tested enough of the sample space that you can confidently, truly say, in this population, in this demographic, this is true with this probability. All right, now, final. The two evils of machine learning, which is bias and variance, okay? So you can create a model that has high bias, which means it really doesn't do much for you, or you can create a model that has too much variance, which means it just follows the data, okay? What you want is you want a model that just fits right. So if you underfit the data, which is, for example, where you had that polynomial and you decide to draw a straight line, you're going to get very high error rates, right? Because those points, the thing you've drawn, does not capture the pattern. Okay? So that's what we mean by underfitting. You underfitted the model. And then overfitting is where you just literally, so decision trees are notorious for this if you do not prune them. Because a decision tree will tell you, you have got 100% accuracy, you are winning at this thing, but it has literally gone on and chased things that are complete outliers about some really weird occurrence that happened at some point. So you actually prune it. Okay. So what you want is you want to find the sweet spot, which is as you're validating your model, as you're training it, so that curve is for the training model, once you get to a point, okay, so the validation performance, all right, keeps going up and you're doing quite well. The prediction error is actually going up. Anyway, I think maybe something is off with my axis. But anyway, so if the validation, once the validation keeps, if you start to get really, really good at getting correct, I think my graph is easy. Yeah, I don't even know if I should keep it. But anyway, but the whole idea behind it is you want to stop. So you've got two things you're testing against. You've got your training set, your validation set, and then you've got your tests, all right? So once, as you are training, if you get to a point where by improving the training result, you are making the test result worse, okay? That means your model is not generalizing very well. It means you're starting to overfit. You need to stop before you do that. That is probably as good as your model is going to do. you need to look at alternatives, which is this model appropriate for this? Maybe this is the time. If you're still not happy with the precision, with the errors that you're getting, then you need to look at another model, another system, or something like that. But by you training it some more is not going to make it any better. Okay, that's as good as you, that's where you should stop. Okay? All right, so to avoid, for example, overfitting, a simple model is always best, okay? So if it looks like a polynomial, draw a polynomial. Don't track all of the points, okay? So go simple first. Throw in more data edit. The reason for this is the more examples it sees, the better it is at capturing the true pattern of the data. All right? Regularize your model, which, for example, means, work with stumps, maybe make the neural net not so deep, make the decision tree a little bit shallower, you cut it off. Don't make it so precise. Add an error tolerance. For example, if you're doing an SVM, add the error, build in an error in there to say, I will stop when the error is at this point. Don't chase perfection. Okay? On the training. Don't chase perfection on the training, and usually you get a better model. So if you see your model performing at 99%, really look into it. Like, that's not always a good thing. It's usually not the best stuff. But anyway, really look into it. You can also use bagging, which is a thing where you train really simple models, okay? So you train with perceptrons, you train with stumps, really simple lines, just a bunch of lines. And then on random sets of data. So you randomly sample the data, run it, train on that, bag it, and then take the average performance of those algorithms, and that's going to be the algorithm that you're going to use. Because each one of those little models will have their own bias, and they'll have their own error built into it, okay? So that's going to let you not overfit on all of the data, because each one of them is only seeing only a subset of the data. All right, to avoid underfitting, once again, let your model be more complex, because obviously, you're just drawing something that's too simple for the underlying distribution. Add more features. So I talked about removing features. Maybe this is the time that you might want to add the features, or go look for more data. Actually, a lot of the time this happens quite a lot. It just means that your data set was not as rich as you would have wanted it. So add in more features. And then, of course, you can always do boosting. And boosting is like bagging, except now you're going to concentrate on where the algorithm got it wrong. Okay, so you're making it stronger. You want to train it on the features that it was getting more wrong. All right, and then of course, generally, yes.
I just want to ask you about that validation set. Is that the simultaneous set where, based on the training, you calculate the error and see how that's doing as well?
Okay, I'm not sure I understand the question.
The validation
Yes.
set, is it a simultaneous portion of your data that you tested, work out the error based on how the training is going on, and
Yep. Yep. So exactly, the validation is the one that you use to improve on the performance of the algorithm as you are training. Okay? So if you think about this as a curve, for example, and you're trying to understand the slope of the curve to sort of know how you should change it, okay? That's the validation set is going to be the thing that affects what your weights are going to be and what the shape eventually is going to look like of your curve.
so it's an additional third. You have training
Yep.
and validation set.
Yes. Yes. So in your training, you're yeah. Anyway. Okay. So anyway, generally, you can say that if you've got a lot of data, you stand a good chance. If you make sure that you've really captured the scope of your problem, you stand a really good chance to have a pretty good result. And with that, really? Okay, all right. So anyway, just a summary about today. All right. So we just wanted to let you guys, I know yesterday's talk was interesting. Some people were like, no, that's too simple. Some people were like, what is this thing? But today we just really wanted to give you guys, this is like entry level into machine learning, give that foundation. The practical is going to do that for you guys, build that intuition as you then move on from machine learning actually to deep learning. Make sure that these things are sorted out. So think about this. You're working with probability distributions. You're working with we are working in optimization spaces, because obviously all you're trying to do is, how do I best reduce the error to get the best performing algorithm, right? And then, of course, we talked a little bit about some of the things like my section, where I talked about just certain things to think about as you're going through this, all right? So once again, some take-home messages. Go in, think about exactly, go back to your probability class or whatever, just go back to and think about that. There's a lot of intuition that is built just from getting the principles of probability, a lot of intuition that's built from that. Then always remember, it's first about the data, sometimes about the features, and definitely also about the algorithm. Okay, so these are the three things that you have to talk to remember. And then, of course, as we will get a sneak peek into today, we'll get an introduction to deep learning. So just take these foundational stuff as you go on to deep learning, into getting more into for the rest of the week. Think about some of the stuff. And that's the end of it for me. And Stefan will walk you guys through some of the expectations for the practical today.